how-to on doing BCA tables. The purpose of this whole calculation is to predict the amount of chemicals needed to react or the amount of chemicals that will be produced at the end of the reaction. So basically this is used, in industry. Eli Lilly would use this to say, I need so much of this chemical to make this product so I can use in another reaction, or things like that. So you start out with an equation, and we are going to use lead mixing with hydrochloric acid. We're going to use lead 4. It doesn't look like it's 4. There you go. 4. So it'll be lead chloride 4, and then 2 H2s. Alright, so we have our balanced equation, and we are told in the problem 4.0 moles of PB, of the lead. So we have 4 moles of the lead. We don't have any information about the HCl. We know that it's going to make PbCl4 and 2 hydrogen gas. And we know that because this is a single replacement, and Pb is the plus ion, H is the plus ion, so they are going to be the ones that do the switching. H can't be by itself because it's a diatomic, so it gets H2, and then we just balance it out. We need 4 Cl's here, so we need to put 4 here, making that 4 H's. To make this have 4 H's, we put a 2 in front of it. Alright, pretty simple on the balancing and writing the equation. No help needed there. Next, we put in what is called the BCA table. So we do the B, C, A, and we make it into a table. So we need some nice long lines here, divided up. Each chemical compound gets its own column. The B stands for before, the change, or C stands for change, and A stands for after. So it's before the reaction, what's happening during the reaction, like the change in number of moles and amounts, and then after the reaction. Okay, so before, we know that we have 4.0 moles here. We were not given any information about the HCl, so that is excess. Okay, I would imagine what is happening with this reaction is that they're taking little pieces of lead and they're just plopping it into a container of HCl and letting it react. You will have some HCl left over, right? Since this is before the reaction, we haven't actually reacted anything yet, gotten any products, so those are both 0 moles. Okay, the change. We are going to take all 4 moles of this lead and we're going to react it. So we will subtract 4 moles here. HCl, for every mole of Pb, or for every atom of Pb, we are going to use 4 atoms of, or 4 molecules of HCl. So we have 1 Pb, and we have 4 HCl. But I don't have 1 atom of Pb, I have 4 moles of them. So if I need 1 of this is 4 of these, 1 mole of this would be 4 moles of these, or 4 moles of this, I'm going to have to use 16 moles of HCl. That's plenty, it's fine, because we have excess, and I'm saying excess, but writing it in a shorthand form. Alright, so I've used 4 moles of my Pb, I've used 16 moles of my HCl. Now to go on to products. So for every Pb that I have, I'm going to make 1 PbCl4. Okay, Well, like I said earlier, I don't have 1 PB, I have 4 moles of PB. So if I do 4 moles of PB, I'm going to get 4 moles of PbCl4. So we're going to add 4 moles of the PbCl4. All right, to do the last one, how many moles of H2 are going to be created? 1 mole of this is 2 moles of this, so we're going to basically take these boxes and pair them up. Okay, 1 of these is equal to 2 of these. Like I said before, we don't have 1, we have 4 moles of it, so 4 moles of these will equal 8 moles of the hydrogen molecule. All right. Next step's pretty simple. You just do some subtraction and addition going down. So after, we're going to take 4 minus 4, we're going to have 0 moles of lead left, which is what we want because we want to react everything. Our excess, we're going to subtract out. 16 moles of it, still going to leave us with excess. Now our moles, we started out with 0, but we made 4, so we're going to end up with 4 moles. And for our H2, we started out with 0. We made 8, so we are going to make 8 moles of the H2. So your BCA table is full, but this problem wasn't exactly asking for you to fill out a table. They want to know information. So if we use 4 moles of PB of lead, how many moles of H2 are we going to get out? How much moles of hydrogen gas? Well, you're going to make 8 moles of H2, and that would be your answer. Okay. Notice that I didn't say 8 moles, I said 8 moles of H2. So our formulas have to be included. Formulas are now a part of units. Okay. This one was a fairly simple example, easy because we could do all of the math in our head. The only difficult one was this 16, but once we drew it out, we saw that 1 of these equals 4 of these, so basically we're multiplying by 4. Let's do one that's a little bit more tricky. So we're going to use the equation 2H2S plus 3O2 goes to 2SO2 plus 2H2O. Okay, sorry, that's a little on the crooked side. We're going to do our BCA table. We are told that we are given 8 moles of H2S. Okay. Draw our nice little table here. We know that we start out with 8 moles. We weren't given any information about oxygen, so we're going to assume that it's excess, which makes sense. I mean, it's really easy to get a hold of oxygen. So oxygen being excess is understandable. This is before the reaction, so we don't have any moles of SO2 and H2O. All right, the change. We are going to lose all 8 moles of this. Okay? Here is where the tricky part comes in. 2 of these need 3 of these. So we need 2 H2S's and 3 O2's. It's not the easy 1 to 4 that we had here. It is 2 to 3. So we need to come up with a way to relate those two together. And we relate that with ratios. So we are going to use ratios. Rations. Ratios are 2 moles of H2S equal 3 moles of O2. So that's the relationship. And I get those numbers from here. We use the coefficients. So 2 H2S and 3 O2s form our relationship. I'm starting with 8 moles of the H2S. So we have 8 moles of H2S, and I need to come up with a ratio to convert between moles of H2S and moles of O2. I want to cancel this out, so I'm going to put these guys on the bottom. So 2 moles of H2S and 3 moles of O2. So they cancel out. I'm going to do 8 times 3 divided by 2, which gives me 12 moles. I'm going to use 12 moles of O2. Right? Some of you may be able to see that in your head, but this will work every time. 2 of these make 2 of these, so that's pretty simple. We're just going to use 8 moles, okay, because I have 8, and it's the same, so 8 and 8. And then the same thing for the water. I'm going to get 8 moles of the water. Right? Do your addition and subtraction, so 8 minus 8 is going to be 0. Excess minus 12, still excess left over. 0 plus 8 is going to give me 8 moles. 0 plus 8 is going to give me 8 moles. Now, again, this problem did not just say fill in the equation. It's going to ask you something. So how much oxygen do you need? Well, we needed 12 moles of O2 to react. Okay, so how much oxygen was used? Well, 12 moles were used. Here's a little hint. Okay, we were trying to fill in this box here, and we were having a hard time with it because it didn't have easy math, simple math. This is what we were given to begin with. We needed to figure out this box. If you notice over here, we multiplied by 3 and divided by 2. So we're going to multiply by what's above that column and divide by what's in this column. So you, a trick take the number given, multiply by the coefficient of the column you want, divide by the coefficient of the column you have. Okay, so for this one, we did number given 8 times the coefficient of the column you want divided by the column you have. It's hard to write out like this, but if you do the pattern, you figure it out every time. So this one, I'm going to figure this one out, multiply the number you were given, 8, by the coefficient of the column, so times 2, divided by the coefficient of the column you have, divided by 2. Okay, this one, number that was given, 8 times 3 divided by 2. So times the column you want divided by the column you have. To figure out this one, 8 times the column you want, 2 divided by the column you have, 2, 8 times 2 divided by 2 is 8. Same thing here, 8 times the column you want, 2 divided by the column you have, 2 gives you 8. So this kind of trick helps. Now, once you have this set and easy, I can give you additional information. Maybe I'm not going to give you moles. And in lab, certainly you won't be given moles because we can't measure moles. We have no device that will measure out moles for us. All right, so let's look at some ways we can use that. Ways, information, oh, it helps if that's on the screen. Ways information can be given. Okay, and what you can do with it. So if say we were doing something in lab, you would be given mass. We would use the molar mass to convert to moles. You could be given a volume of a gas, and you can use molar volume to change to moles, or I could be really mean and give you a number of molecules, and you would need to use Avogadro's number, which is that 6.02 times 10 to the 23rd, to convert it. All right, so we can do an example of one of those. So our equation, 2 moles of silver nitrate, AgNO3, plus magnesium bromide goes to 2 molecules of AgBr plus MgNO3, 2, magnesium nitrate. Okay, and I tell you that you are given 22.5 grams of silver nitrate. Okay, well, in our BCA table, we cannot put grams into our BCA table. BCA is moles only, please. BCA is moles only. So we have to convert this to moles before we can put it in here. And that's pretty simple to do. You just divide by the molar mass. So 22.5 grams of AgNO3 times 1 mole over 1.6 or 169.674 grams. Our grams cancel out, and we are left with 0.133 moles of AgNO3. This number we can put into our BCA table, 0.133 moles. Since only moles can be in here, it's redundant to write this over and over again. It's just assumed that everything in here is moles. We know that this is excess, and we would have 0 and 0. So our change, we're going to subtract 1.33 moles. To figure out what we're going to do here, we're going to take this times 1 divided by 2, and we come up with 0.665 moles. We're subtracting it because we're getting rid of it, we're using it. We will then, since this is 2 and 2, this would be a plus 0.133, and then again we have this times the coefficient divided by the coefficient. We would get positive 0.66. Do our math, 0, excess 0.133, 0.0665. So if I ask you then, after you have this table, I can ask you lots of stuff. I could say how much MgBr2 is used. I could ask you how much silver bromide here is produced, and I could also ask you how much MgNO3 is produced. I'm going to ask you how many grams of AgBr are you going to get in your reaction. So you're going to take this number, which is in moles, and I want grams, so just do another conversion. 1.33 moles of AgBr times, and we're going to put the molar mass on top this time because we want to get rid of moles. So cross out your moles. 1.33 times 187.774 gives us 24.97 grams of AgBr. Alright, so If you do out this reaction and you use 22.5 grams of AgNO3, you are going to get, in the end, 24.97 grams of AgBr out in the end. All right? This is almost the most complicated problem that you will come across in BCAs, but simply it does have quite a few steps. All right. Any questions? Come and see me in class.